this case, we're asked to prove that A over sin A is equal to B over sin B, which is also equal to C over sin C. So that's if we're given a triangle with sides of length A, B, and C, and opposite these sides, we have the angles A, angle B, angle C. The small a, b, and c stand for the lines, and the large A stands for angle A. Similarly, the large B, angle B, and the large C is angle C. So the sine rule is one that we're going to be using a lot in our practical trigonometry as well. So it's handy to understand where it comes from. So for the sine rule, if we're going to prove this, we have to consider two cases. So we have to consider a triangle where we have an acute angled triangle and also an obtuse angled triangle. So in the first case, we're going to consider our acute angled triangle. So acute angled triangle. So we draw a triangle. So in this case, we're going to call this angle here A and this angle here B. So in this triangle, B is acute, but in our next triangle that we're going to draw, B will be obtuse. So in this case, we're going to draw, so this is going to be a perpendicular here down to this line here. So that's going to be a right angle. And this, we're going to call this H. And then we said that angle A was opposite side A. So this is side A. Angle B is opposite side B, and then this here would be our angle C, but we're not actually going to be using that in this proof in particular, but we could also then go back and use C, but for now we're just going to be using angle A and angle B and side A and side B and H. So the first thing that we're going to do is we're going to get sin of A and we're going to get sin of B. So sin, which we can get from our log tables, is the opposite over the hypotenuse. So for A, the opposite is going to be H and the hypotenuse is B. So sin of A equals, because we can only do sin, cos, and tan in a right angled triangle, this has to be the triangle that we're using for A. We can't say that this is our opposite because that wouldn't be treating this as a right angle triangle. We can only do sin, cos, and tan in a right angle triangle. So sin of A is H over B. So then we're going to just get everything in terms of, so we're going to get it expressed in terms of H. So so the H here stands for the height. Sorry, that's a bit confusing. So I had H as hypotenuse here, but H in this case stands for height. It doesn't stand for hypotenuse. Our hypotenuse here is B. So hypotenuse there, and H is also the height here. So I got my H here from, that's where it comes from. So I'm going to get this in terms of the height. So height is equal to, so I'm going to multiply both sides by B. So B sin A. So now I have so the height in terms of the other variables. So and then I'm going to get sin B. So sin of B. So we know sin is opposite over hypotenuse, but we have to treat it as a right angle triangle. So when we have a right angle triangle here, our opposite is going to be H again, so standing for height, and our hypotenuse here is A. So then we're going to get this again in terms of H. So H is equal to A sin B. So now we have our first one in terms of H and our second one in terms of H. And because they're both in terms of the exact same variable, so H is equal to this and H is equal to that, we can let those two equal. So let H equal to H. So we're letting this equal to this. So we let B sin A, which is from here, equal to A sin B, which is from here. So now that we have this, so we're going to label that equation 1. Now we have to go on to obtuse angled triangles, because we have to prove that the case is true for obtuse and acute angle. So in the last one, we had angle B was acute, But in this case, we're going to have angle B as an obtuse angle. So I might... So in this case, where this was angle A, so in our last one, angle A was in this area. So this is going to be angle B, so we can see it's an obtuse angle. And opposite angle B, we have side B, and opposite angle A, we have side A. And as in the last one, the height, or the perpendicular height, say in this case, we're calling this H. But because this here is a straight angle, we can call this 180 minus B, because 180 there's 180 degrees in a straight angle. So what we want to do here is the exact same as we did in the last one. So we want to get sin A and we want to get sin of B. So sin of A, so when we're getting sin, cos and tan, we have to consider it as a right angle triangle. So this here is the triangle that we're using, but I'm after extending that to get, in order to get sine, so I can have created an extension of a right, to have a right angle triangle. So sin is opposite over hypotenuse. So H here stands for height, so that's our opposite. Our angle A, so that's opposite, and our hypotenuse is B. So if we want to get this in terms of our H, we multiply both sides by B. So H is B sin A. So now if we want to get, so for B here, we don't really have that in terms of a right angle triangle. So we can't exactly directly get the sine of B, because it's not really expressed. In order to create this make this into a right angle triangle, we'd have to edit it like a little bit more. But we have 180 minus B, and that is in terms of a right angle triangle. So if we were to get the sine of 180 minus B, so that would be opposite over hypotenuse. So opposite is H, hypotenuse is A, and then if we want to get H by itself, it will be A sin 180 minus B is equal to H. And so when we have, then we have 180 minus B, but 180 minus, so say if we have our unit circle and we have an angle, say an obtuse angle here, 180 minus that obtuse angle is going to be this acute angle here, but that is going to be the reference angle anyway. So the sine of the reference angle would be the same as the sine of the obtuse angle. So we can say that the sin of 180 minus B is equal to the sin of B. So we are letting that, instead of sin of 180 minus B, we can write a sin of B is equal to H. So now we have H equals this and H equals that, so we're going to equate them. So let H equal H, so B sin A is equal to A sin of B. And now this is what we have then, and this is exactly what we had in the last part of the question. So in the last part, we had B, so this is the part where we had our acute angle triangle. We had B sin A is equal to A sin B, so we just have the exact same thing here. So now that we've proven that statement for acute angle triangles and obtuse angle triangles, so this is true for acute and obtuse, we can then rearrange this. So what we can do is we can firstly, so we can divide both sides by sin B firstly. So B sin B sin A is equal to A. And then we can divide both sides by sin A. So then we get B sin B is equal to A sin A. And now we have almost proven our sine rule. So we've gotten to here, but another part of the sine rule was to show that that is equal to C over sin C. But if we were to drop, so if we drop a perpendicular to the side B, so the perpendicular was the H that we dropped. So if we were to drop a perpendicular to the side B, we would be able to prove, we can show that A over sin A is equal to C over sin C. So similarly, we can show this. So then we have ultimately showed that sin A over A is equal to sin B over B is equal to sin C over C. So that is a sine rule. So we have to remember that in the sine rule, where there are two cases that we have to consider. So we have to consider acute angle triangles, and we have to consider acute obtuse angle triangles. And the statement that we're proving for obtuse angle triangles is the same statement that we want to prove for acute. And then when we've shown it's true for obtuse and acute, then we have pretty much almost proven, and then we just have to state that it's going to be equal to, because we have shown that it's true for angle A and angle B and side A and side B, so we just have to say similarly it is also true for angle C and side C. So that is our sine rule. So that is trigonometric formula 2.